Okay, our next speaker is Andreas Stefik from the University of Nevada in Las Vegas. Andreas is going to be talking to us about evidence-based computer science education.
All right, thank you very much. Before I start, let me just say thanks for the invitation. I was really excited to come to this just because accessibility and talking about evidence, which Roy asked me to talk about, is sort of near and dear to my heart for sure. So my name is Andreas Stefik. Almost everyone calls me Stefik. I'm going to be talking about evidence-based computer science education today. To sort of give a sense of my own bias, I guess, or my own sort of background, I'm a computer scientist by trade, so unlike Steve, I'm on the opposite side. I don't know almost anything about hardware, but I do know stuff about software, so it's sort of the opposite. It's interesting. And I invent programming language tools and a lot of the infrastructure that kind of goes around them. But what I study is accessibility sort of on top, and then how these technologies are impacted by people and the evidence that we use to sort of understand that. One of the technologies that I invented along with my wife a number of years ago is called the Coleman programming language, which is used pretty heavily around, especially the United States. And if you can't see the picture because you have a visual disability, there's a wonderful picture of my 2-year-old daughter who's sticking out her tongue. It is quite adorable. Okay, so first of all, let me just sort of mention what I mean by evidence. And when I say evidence-based computer science education, what I'm really talking about is one piece of it, because computer science education means a lot of things, right? Computer science education lives in a context, and so does accessibility. You know, there's lots of things that can impact people when we're talking about students in the classroom or students right as they get out of high school or college or grade school or whatever they're doing. And what I'm going to be talking about today is really one piece of that, and that is the programming languages and the tools that people use as part of that. Now, that's just one part of computer science education. It's not the whole. But as I'll kind of explain, it is actually pretty important to think about. It's just not the only piece. So there's also curriculum, scaffolding, good teaching, and all sorts of other factors that impact computer science education as well. So let's kind of take a step back in time and think about sort of where we've come from in terms of programming. So on the screen right now are sort of two ideas. One is a little console and another is a text editor. These might seem like they're not sophisticated, but in fact, actually, these are very complex and very sophisticated environments. It's just that nowadays we've mostly moved on, and so we have a lot of computer programming environments exist both for professionals and otherwise. So on the screen right now is a picture of a technology called Quorum Studio, which is actually a programming environment that is often used by students in high school. But it's also very accessible even to people that can't see. So there's game editors built in. Somehow we've made all the graphics blind accessible and stuff like that. And on the slides, there's a video we have on there that you can see if you'd like to later that shows how that works. Now, besides that too, computer scientists sometimes forget that computer scientists aren't always the target audience, right? So on the screen now is an environment called RStudio, which is a technology designed specifically for people that do data science. And data science is fascinating. On this image, you can actually observe that it's really just a console. It's actually pretty old school what RStudio is. You kind of type code in this console and it gives you some information in real time. But it also includes different kinds of features that maybe computer scientists wouldn't thought about as much, like including the data sets in them and understanding the history of those data sets and stuff like that, which is all kind of built in. And data scientists aren't the only one either. So on the screen now is a picture of what's called Unity 3D. And Unity 3D is a fascinating environment for computer gaming. Sort of long gone are the days where you might just fire up a graphics engine and write your code in, linear algebra. That you could do that, but it would be very difficult. And in an environment like Unity, there's all sorts of properties on the window. You can visually drag and drop things. There's a lot of accessibility challenges here, although they're all solvable. Making 3D graphics, even blind accessible, is absolutely possible. It's something I've been working on for quite a while. But the point is, an environment like Unity caters to a different target audience that is still very much so programming related. And then finally, in the United States, at least, and I know it's true in the and some other countries, students are increasingly doing computer programming at very young ages. So, for example, in Nevada, there's a law that I helped pass called SB 200, which basically makes it so that children between ages 5 and 18 are required by law to learn computer programming, just like you would learn math or English or something else. And there are lots of environments for these young kids with lots of challenges, many of which are accessibility. On the screen right now is a picture of Snap, which is actually not accessible, but it's an example of a block language that you can use at. So here's sort of the big picture point. In the last 40 years or so, computer programming has changed a lot, and it hasn't just changed in a linear way. It's changed depending upon like what community you're targeting, what that community needs, and that sort of idea. But the question is, what evidence is actually guiding these change processes, and what does that mean? And why do we care about that? Well, it turns out, if you look at just computer programmers, paying software developers, maybe not too surprising, is actually pretty expensive. So there's different ways you can cut up the data, and different sources give slightly different numbers, but a reasonable estimate, I think, is around $331.7 billion in wages per year in the United States alone. So what this means is, when we actually train computer scientists, all the teachers that we train, we have to pay those people, all the students, all that sort of stuff. All these people have to effectively learn in programming languages. So the moment any of those change, we have to modify all the curriculum. We have to retrain all the teachers. We have to retrain all the developers. And at $331.7 billion a year for just the developers alone, that gets pretty expensive pretty dang fast. So, but the question is, what does it even mean to sort of gather evidence on these kind of technologies? Well, funny thing, I imagine many of you might be familiar with this whole idea of a quote unquote pandemic. Well, it turns out that historically, before we had sort of the marvels that we have today, you know, a vaccine in just a year or so, hopefully, back in the day, in the early 1700s, there was a lot of claims that were made that were largely done subjectively. So one of the more famous examples is in the early 1700s, there were these two fellows, one of which, Cotton Mather, was arguing for effectively to inoculate, I won't go into the details, but basically give people smallpox. And another fellow, William Douglas, was like, whoa, that's wicked, that's criminal. And if you read the literature, neither of these people were right, and neither of these people had any evidence whatsoever for the kind of claims that they were making, even though it turned out that Cotton Mather was sort of kind of right, given the situation that he was in, although it's complicated. So you might say, okay, cool, great example from the 1700s, but what about today? Well, it turns out that even at places like the Department of Defense, this happens still relatively recently. So in the 70s, there was this wonderful DARPA meeting, and DARPA had set up something on programming languages and estimated about $3.5 billion a year was going into the design of these things because they kept changing, different devices had different languages. And we essentially saw the same kind of idea. A fellow named David Grease argued, our first speaker talked about having variables which can contain procedure bodies as objects. The question is whether or not it is a reasonable thing to have in a language. And others disagreed. And you can argue maybe whether or not those positions are right, but in fact, as it turned out, there was effectively no evidence being presented, not just there, but there wasn't even any that existed at the time, and I'll get to that in just a second. So then what does it mean? So it turns out in other fields, a series of innovations started happening in the early 1800s on what it meant to be sort of evidence-based. One of the most famous examples by the early 1830s was this thing called the Nuremberg salt test, which basically asked the following questions. Did the experimenter manipulate the experiment? Basically, did anybody commit fraud? Did the people understudy deceive themselves? Like, are the people that designed this thing, do they just think it's right? And then if there was a treatment, like I gave them some kind of technology or whatever it was it actually a fair experiment? Was this a fair comparison? the Nuremberg assault test, in sort of historical irony, was actually spawned by the homeopathists, which basically disproved themselves over time, which is interesting. And this has gone on for a long time. So by the early 1900s, there were these fellows, this fellow named John Stokes, who started arguing we needed to standardize procedures across research groups by the 1930s or so. And they would talk about selection and classification, treatments across groups. The idea being, we don't just need individual experiments, we actually need different research groups that may have competing interests to see if they can get the same answer and to collect data in the same ways. And this ultimately led to a very famous study that I imagine all of you know, even if you don't know it, and that is the famous study by Austin Bradford Hill and Richard Dahl, notably, which was the first, well, not the first, but one of the first randomized controlled trials. I've heard a million claims about this idea, randomized controlled trials, and so let's talk about it for just a second. Number one is this idea of randomized controlled trials use both lab data and epidemiological data. They use statistics, but they're not fully quantitative or qualitative. They can do both. They have multivariate models. They have different kinds of standardized procedures. They have effectively a large series of checks and balances that are built into them to prevent fraud and correctness, stuff like that. And all of you probably know this result because you know that smoking causes cancer, and that's where this comes from. So this particular technique, interestingly, set up such a revolution in that field that it caused an 11.2% increase in the number of RCTs per year for like half a century. So I mean, can you even imagine? I can't. That like you have an innovation so important that it caused exponential growth in the type of methodological evidence used across an entire field. Nowadays, these kind of studies in other fields, specifically education and in medicine, are required by law because they're so commonplace. Now, interestingly, you might be thinking, well, okay, cool, but what on earth does this have to do with computer science education? Well, it turns out computer science education and education broadly has been changing in part because of changes to the law, specifically an act passed by the Obama administration before they left, requiring randomized controlled trials as part of the What Works clearinghouse. And today, one of the top journals on computer science education, Transactions on Computing Education, has also adopted formalized evidence standards, or they call them reporting standards, as part of the peer review process. In other words, they're trying to promote the idea that we need checks and balances in our evidence processes. Notably, they use one called APA JARS, but there's others like Consort, What Works clearinghouse, that are used by a wide variety of journals across many scientific fields for good reason. Okay, so at this point, what we've mentioned is we know that there's been a long history of kind of designing these tools and languages, and that we know that a little bit about evidence and what it means in the context of other fields. So what's actually been going on in programming languages? And what do we kind of know about computer science education there? Well, what we do know, we know a few things. Number one is there's thousands of programming languages, thousands of these things. And they often have their own syntax, their own semantics. They have giant standard libraries often. They often have their own user communities, context of use, and tools. And in terms of accessibility, this is especially challenging because if you write accessibility code on a Microsoft platform, that code is 0% compatible with the code on Apple platforms. And then that code is 0% compatible on the web and on Android devices and on other devices, et cetera, et cetera. That's a huge problem because it means you basically have to write things for accessibility across many operating systems, platforms, programming languages, standard libraries, just to make sure that a kid that is blind or has some other impairment, some other disability, can actually participate in a meaningful way. So the question is, did we do this based on some kind of evidence? And it turns out the answer is no. There was a famous study now by a fellow named Antti Hanikka-Janaho in 2012, and he showed basically that between 1976, around the time of that DARPA meeting, and 2012, there was actually only 22 experiments that could be considered reliable. To put this in perspective, other fields have in the range of hundreds of thousands of studies for things that matter, like when death is on the, or let's say $300 billion per year. And it turns out part of the too is even when computer scientists are gathering data, There's a study by Amy Coe, Tom Latoza, and Margaret Burnett showing evidence that they often miss things like having a control group, testing people other than themselves when they write an academic paper, and even the idea of collecting data at all is not always included in academic publications that supposedly go through a rigorous peer review process. So before 2012, and just in general, we didn't really have a lot of data about these things, but we know that anytime these language products change, we have to build entire infrastructures at great expense in order to manage it. So we make a new block language, all the documentation is brand new. We make a new programming language from some company, all new documentation at great expense. So what do we actually know about these tools, and what can we do over time to make changes so we see some condensing of these products to be more evidence-based? Well, we do know a few things now. One is there's this concept of static typing. It's basically the idea is that if I have a variable in my code, I have to say what it is, like this is an integer or a number or something like that. It's a minor thing by any standard, but it turns out programming languages have varied this for quite a long time, and nowadays there are randomized controlled trials done in multiple countries, under multiple conditions, studies with and without development environments, studies by other groups like at Microsoft on TypeScript, which found similar answers, studies on variations on it like generics or other things. And the general consensus is that this idea of static typing actually makes programmers faster. And we know it explains about 14% of the variance between developers, ballpark. So that's number one. Number two, it turns out in the 60s or 70s or these kind of areas, we developed this syntax that was designed in the original programming language C. And this syntax needs to go away. It needs to be deprecated for evidence-based choices. Notably, C used lots of terminology that really didn't have a foundation of evidence. And how could it have? Because they couldn't have known exactly what studies would show 40, 50, or 60 years in the future. And a lot of the decisions that were made were things like we use the word for to represent the concept of repetition. Both block languages and text-based languages use this kind of terminology. And words like that compared to others like the word repeat, which is actually semantically meaningful, make a difference. So on the screen is one example of a study where the programming language, several programming languages were compared to this idea of a placebo language. The idea being, in my lab, we generated computer code randomly using random symbols, and we compared them to other languages like Java or Perl or languages like that. And it turns out some programming have syntactic choices based on C that are effectively so bad for novices that randomly generated choices do just as well in the studies, which was kind of shocking when we first found it. So besides that, there's also easy things that we know about too. For example, many programming languages generate error messages when they have a problem. This is not unique to text-based languages. Both text-based, block-based languages have errors in them. This is a fact. And it turns out that these errors, the kind of mistakes humans make, are so predictable that they can be derived through a formal equation with an exponential decay model. And one of my students found this relatively recently. And this is fascinating because what it means is if you look at reports like the IDICE report on compiler error messages, it turns out small changes to the words generated by these languages don't require any documentation changes, not really, at least not to the core language. And it turns out we can predict very accurately what problems humans have, and we know the distribution, so how heavy people have these problems. And it turns out it makes a big difference. Off the top of my head, I want to say something like 10 to 20% difference in terms of your productivity for relatively younger individuals. So what about other areas? Like we talked earlier about data science, and it turns out the data science community has made a whole bunch of attempts to try to make data science easier. And unfortunately, a lot of these have not been all that terribly effective. So there was a study on the use of this concept called tidyverse in R. The idea is, one, making things more consistent, which I imagine helps, although it has never been tested. But number two, they made a lot of changes to like small syntactic variations in the programming. And it turns out these things didn't really help that much. And when you look at the data, what it seems to indicate is that we really need to rethink data science just like completely. You know, like maybe we shouldn't name every statistical test after an old, dead, white mathematician. You know, instead of Bonferroni, we could come up with a semantically meaningful set of names. And besides that too, there's lots of specialized programming environments. So for example, if you're programming on a GPU, the company NVIDIA made libraries to try to make that easier. But it turns out, because they also didn't use evidence as their design part of their design process, they basically missed the mark in terms of like making it easier. That largely just because it was never tested. It was just people kind of guessing or taking their good faith estimate. But evidence on that sort of idea, just kind of making good faith estimates, seems to indicate that you need a little bit more oomph, a little bit more evidence in order to get this right. So you kind of need, for something as complex as GPU programming, you kind of need to have data to back your assumptions as opposed to just kind of guessing. Now this gets even crazier. So for example, in programming today, it's often really common to just use multiple programming languages at once. In 97% of open source projects, it turns out they do this, and you can imagine why. Like you might use JavaScript on the front end, PHP on the back end, an SQL server to represent the database, CSS for formatting, and then HTML to represent your particular presentation. And this is insane. This is absolutely nuts that we've just decided that we're just going to dump tons of programming languages in at once, assume that they all do a good job, and then call it a day. And so we've been evaluating this empirically to try to find out if this makes sense. And of course it doesn't. But the thing is, oftentimes what you find is relatively surprising. Like it turns out in one of the studies that was published recently, if you adjust the materials in terms of this polyglot approach, you can make small little changes to it, and it actually really significantly improves the situation for novices without hurting professionals in any way, shape, or form, which is pretty interesting. But you can't really understand this kind of work without like a good grasp of how randomized controlled trials work and the statistical methodology and stuff like that. Now you might think too, well, why don't we just switch to blocks? That'll fix it all. It's a magic wand, right? Well, it turns out the studies on this show that it does help. But it turns out if you look at the data, they have this score called a Cohen's d, and it's about 0.4. What that really means is that it helps, just not very much, even for beginners. So in addition, with block-based programming languages, there's also quite a few accessibility challenges that need to be hammered out. And these are really important because at K through 12, it's actually required by law that students can use anything in the classroom. So in Nevada, you can't actually use technologies that aren't accessible because it's illegal, right? So you have to actually manage that kind of stuff. And it makes sense. These kids have civil rights, anybody else does. Okay, so that's a lot. So the broad purpose is that when we're designing the technologies that form the core base, all our curriculum, all our designs, we really need to base these decisions on evidence. And I identified a few based on the literature that include deprecate C-style syntax, improve error message design, which we know how to do, use static typing in all these languages. I didn't put it in the slides, but there's this concept called lambdas, and the jury's kind of out on them. Polyglot seems to be making things worse. We need to rethink data science almost completely from the ground up. When we make API abstractions for libraries, we need to use evidence for them. You shouldn't just guess because it's really easy to get wrong. We should use blocks in our programming languages, but we need to make them accessible. And then for accessibility in general across the board, we need to make everything everywhere accessible as part of these programming languages in a more consistent way, make it a lot easier. And on the quorum programming language, this is kind of the heart of what we do. We make adjustments to the technologies based on the data that's coming out in the literature and that we gather ourselves. Okay, so that's a lot of words, but if you're interested in any of that stuff, there's the Quorum programming language is at quorumlanguage.com. I included on here a video of our new tool called Quorum Studio, which is actually solves what's called the accessible graphics problem. Basically, you can do any kind of graphical content. You can even use it blind. There's a video on how to do that. I'm also part of the Access CS for All group along with Richard Ladner. There's a URL up on the screen on that. And then you can hit me up on Twitter at Andreas Stefik, and that is all. So thanks for your time. I really appreciate it.
Thank you. Steph, is it okay to call you that now?
Yes, sir. Stefik is what everybody calls me.
All right, Stefik. We do have a couple of comments in the chat window. The first one asks, people often have very individual needs based on their particular combination of disabilities. How can one hope to get a large enough sample of a people with a particular impairment to conduct a proper RCT?
That's a wonderful question. And it turns out that when you're talking about individuals with disabilities, you often can't. And that's just the truth. So like, let me look at, if we go back to this particular slide here, when we do some of these studies, we do comparisons across averages of people that don't necessarily have particular impairments. So in this particular design, there's 3 graphs on the screen, 3 different experimental groups. And then in each, there's this thing that says hybrid, string, and object. And then there's groups of freshmen, sophomore, juniors, seniors, and professionals. We can do that because there's a number, the average across these people happens to be pretty similar. But this gets really tricky with disabilities. For example, what is the average blind person, right? Well, that it's almost doesn't even make sense, because if you have a particular user that's blind and one of them can't see the screen at all and uses a screen reader, well, that person is very different than someone that has like color impairments or other issues like that. So RCTs are not magic. They're not a silver bullet. They're really useful for some things, but when you want to do work with people with disabilities, sometimes N=1 studies are really appropriate, where you work with one individual or one person, or sometimes different kinds of field analysis can be really useful. In other words, at the end of the day, you want to use evidence, and RCTs are really important and useful for language design, but they're not the only technique you need. And so that's really important, especially for people with disabilities.
Great. All right, we've got one more question, and I think just enough time for you to answer it. In your studies, have you found that programmers who started out in text-based programming and were later introduced to block-based came to prefer the block-based format? I'm asking since I personally started out with text-based and I can't see myself comfortably switching to block-based.
Yeah, so that's a good question. So the leading expert on this issue is actually named David Weintraub. He's done quite a few studies on this issue related to swapping back and forth, and also this issue of like whether it's effective and those sort of concepts. I couldn't tell you whether or not you know, this sort of longitudinal thing, because I don't think that's ever been evaluated in the literature. But David did do a really wonderful slides, but he did a wonderful study on watching students kind of flip back and forth between text-based and block-based programming languages. It's from a few years ago at the SIGSI conference. And basically what he found is that different people vary a lot in terms of their preferences. But the result from that study, at least in my head, my interpretation of it, is that adding blocks to a programming language needs to be optional, because people will have different preferences, and that's probably okay, and it seems to fit with the evidence. In other words, I don't think you should force people to use block-based modalities, but having it as an option has been shown to increase learnability by a Cohen's d of 0.4, which is not very much. In other words, it's not a huge effect, and if it's optional, then it seems like it does still work, according to Weintraub, as far as I can tell.
Great. Okay. Thanks very much, Stefik. Someone else posted another URL for additional context if anyone would like to check that out. Oh, hang on, I think there's one more question. Here, I'll read the last question, but you'll have to answer it really quickly because I don't want to eat into the next speaker's time. How do you anticipate managing the need to maintain high standards for innovations in education accessibility with the desire to innovate and iterate quickly? With the rate of growth of software changes, how can developers be encouraged to take the time to make tools accessible? Where is the incentive for the time commitment? And you've got 90 seconds to answer.
Yeah, no problem. So this is actually a great question, and it's really a challenge, including for my group. So for example, we can't run a randomized controlled trial on everything. It's not possible. There's hundreds of thousands of studies that you could run. They're not all equally matter, and there's no incentive to do that anyway for companies or individuals. But the question is, which things would cause the most pain for industry and education by having them change? For example, if all of a sudden all the looping structures change, that impacts every curriculum everywhere for computer science education. So what you want to do is you want the studies that are done to be thinking about this impact, this broader impacts argument of where it impacts across the board. In other words, when we're designing stuff in a language like Quorum, we do lots of studies that can impact the whole infrastructure to try to prove ourselves wrong. But when we're designing like a library or trying to be innovative or add it to a certain or something like that, we don't run studies on every detail because we know we're targeting a smaller group of people. In other words, what I think it should be is the more people it impacts, the more evidence that you should have. And I think that that kind of jives with what you observe in other fields like medicine and education and stuff like that. That's why the FDA has a tiered model, basically.
All right, super. Thank you very much, Stefik, and thanks for the really interesting talk. Very much appreciate it.
Thank you very much. I appreciate it.